So now we're going to begin chapter 20, which is on electrochemistry. And in order for us to, really work well in this chapter, we're going to want to review our oxidation numbers. So this is from Gen Chem 1. In our book, I believe it's somewhere in chapter 4. So if you want to go back and review that, that's great. We'll do a little review here as well. So let's remember our rules for assigning oxidation states to atoms. Remember that anything in its normal elemental state will have an oxidation number of 0. So for example, hydrogen or oxygen or aluminum or fluorine or zinc, anything that's not charged and it's by itself will have an oxidation state of 0. Remember that simple ions, for simple ions that is, the oxidation number is equal to the charge. So for example, sodium chloride we have +1 and -1 because those are also the charges of those. So the oxidation state of sodium is +1, the oxidation state of chlorine is -1. Remember, for simple ions, that's always the case, even if there's other polyatomic ions in there as well. For example, with sodium phosphate, the sodium will still be +1 because it's a simple ion. The phosphate, however, we will have to worry about by looking at further rules. Remember also, these rules are hierarchical, so they will always follow the order. Number 1 takes priority, then number 2, then number 3. For compounds, the sum of all oxidation numbers must equal 0. For polyatomic ions, that is only if we are looking at the polyatomic ion, not a compound. So compound takes priority, then polyatomic ion. The sum of the oxidation states will equal the charge. For example, well, we're going to need rule 4 before we do an example for rule 3. But for rule 4, we want to follow the following order. Fluorine is -1, hydrogen is +1, oxygen is -2, and then ... The ... is there to remind us that we assign oxidation states as preferred charges. Preferred charge based on electronegativity. Electronegativity. So the more electronegative atom will get its preferred charge. For example, technically after oxygen would come chlorine, which would be -1, and then nitrogen, which would be -3. So you'll follow preferred charges as you go through this. And that's generally the rule of thumb. And these are to be done in order as well. So fluorine must always be -1. Hydrogen should be +1 unless it's a simple ion, because rule 2 takes over. So for example, something like sodium hydride, +1, -1, they're simple ions. We don't have to go further. So let's look at rule 3 again. It says for compounds, the sum of oxidation numbers is 0. For individual polyatomic ions, the sum of oxidation numbers is the charge. Let's revisit that. So for something like sodium phosphate, the sodium has to be +1 because it's a simple ion. The phosphate, though, we don't know. Rule 3 tells us that the sum of the oxidation numbers must be 0. So we'll set up a formula. We have 3 sodiums plus phosphorus plus 4 oxygens equals 0, because this is a compound. Sodium phosphate is a compound. It is not a polyatomic ion. Phosphate is, but sodium phosphate is not. So always pay attention to what you're looking at, what species. And since sodium phosphate is a compound, its oxidation numbers must equal 0. And we know that sodium is +1. In order to solve this equation, we're going to need 2 variables solved for. We've already got sodium. So when all else fails, we now look at rule 4. Do we have fluorine? Nope. Do we have hydrogen? Nope. Do we have oxygen? Yes. Let's plug in oxygen. We have sodium already. Do we have enough information to solve this problem? Yes, we do. We can figure out the charge of the phosphorus. So we have 3 plus negative 8. If you do the math, you'll see that phosphorus is plus 5. And remember that we're always going to report the oxidation numbers for one element, one atom. Each sodium is plus 1, so we're going to indicate its oxidation number is plus 1. We're not going to say plus 3. 3 is from the coefficients and the subscripts. We don't deal with that. Each sodium is plus 1, so we say its oxidation number is plus 1. For phosphorus, its oxidation number is plus 5, and for oxygen, it's minus 2. This is all unique to this molecule, or compound rather. Your oxidation numbers can vary in different contexts. For example, if we had sodium phosphite instead, we would see that phosphorus would have a different oxidation number, and it would be plus 3 in that case. But the point is here that we're going to want to calculate ones that we don't know offhand. We can do another one. If we just look at phosphate by itself, now we're looking at only a polyatomic ion. We will say that the sum of these will equal its charge. So 1 phosphorus and 4 oxygens is minus 3, because that's the charge of the phosphate. We now look at rule 4, no fluorines, no hydrogens, next is oxygen. So we should give oxygen its preferred charge. And indeed, if you do the math, you will see that phosphorus again ends up being plus 5. And that should be the case, because it's the same phosphorus that's present in sodium phosphate, the same oxidation state there. So just something to remember. One more, if we take a look at a chemical equation, remember for oxidations, redox stuff, you do not need to balance the equation. You can just go as is. So we're going to assign the oxidation states for everything in this reaction. So let's look at hydrogen. Hydrogen is an element by itself. Rule 1, elements by themselves are 0 for oxidation state. The next we have is water. We're going to want to calculate that. We'll see that we have 2 hydrogens plus an oxygen equals 0, because water is a compound. This is a molecular compound, so we don't have ions here. So, fluorines, nope. Hydrogens, yes. So we'll plug in the 1 for hydrogen. We have enough to solve for oxygen, and we get oxygen as minus 2. Remember that oxygen is not always minus 2. For example, in hydrogen peroxide, oxygen will be minus 1. So you will still want to calculate, although most of the time oxygen will be negative 2. So that's what it looks like in an equation. And remember now, we can identify species that are oxidized and species that are reduced within reactions. And that'll be the topic of our next video.